Hi, welcome to me313 Mechanical Engineering Thermodynamics. Topic of this video are the Maxwell relations and the Clapeyron equation, and the sections in the textbook are 12.2 to 12.3. So here are the three learning outcomes. At the end of this, you'll be able to recognize the four Maxwell relations, and you'll understand where they develop from. You'll be able to use a Maxwell relation to arrive at the Clapeyron relation, and then you'll also be able to use the Clapeyron relation along with PVT data to estimate the energy of vaporization for that substance. So first I want to talk about the Maxwell relations, and we're going to kind of develop these with some calculus, and the important parts here just to recognize where they originate from. So first I'd like you to take a second and look at these two equations and think about, do you recognize those? Because you've seen those before. And hopefully you do. This one right over here is the first TDS relation, and the second one is called the second TDS relation. And we developed those in Chapter 6, and we used those because they were ways for us to go ahead and determine changes in entropy. And they were pretty useful tools. Well, we're going to use those here in a moment, but before I do that, I want to introduce two new properties. And they're called the Helmholtz energy, or the Helmholtz function, and the Gibbs energy, or the Gibbs function. So this one right over here is called Helmholtz, and it's usually given the symbol A, and this is the Gibbs, and this is given the symbol G. And I've written them here with this triple equal sign because these are really just definitions. This is similar to like we just said when we said enthalpy is equal to U plus PV. We just kind of defined enthalpy that way because it was a convenient grouping of terms. Same thing applies with these other two thermodynamic functions. And you'll see these more later in this course, particularly the Gibbs energy. But now just kind of recognize they're just a grouping of thermodynamic terms that are just a little bit different than enthalpy. Right? Now, what I'm going to do now is I'm just going to do some calculus. I'll do some calculus on the Helmholtz energy. And I'm going to take the total derivative. And so dA would be equal to du minus TdS minus S dt. Just some calculus. I could do the same thing with Gibbs energy and say dG is dH minus T ds minus S dt. All right. Now I could go ahead and substitute in for this du right there, the du relation from the first TDS relationship, and then I could take the second TDS relationship, substitute in here with dH, do some simplification. And if I did that, I'd end up with these two equations here I show in green and in purple. And they kind of look like TDS relations where we've got this dA term, but they're just subtly different. But the most important thing I want to show between all four of those colored equations is that they all have this general form that we saw in the previous video, where we had dz is equal to mdx plus ndy. And so we saw that for continuous functions, which all thermodynamic ones are, we could have this second relationship that I show on the right, with in terms of dm dy at x is equal to dm dx at y. And there's something pretty convenient I can do with that. And so let's take a moment. In fact, let's go up and look at the first TDS relationship, the one I have up here in red. All right, and let's look at the substitution. Let's go ahead and draw the analogy between that and dz. So what I'm saying, for example, is du would be the same as dz, so then t would be the same as m, ds would be the same as dx, etc. And now let's go ahead and develop the equation dm dy at constant x. Well, that would be dt over, well, dv at constant s. All right, and so if you kind of keep doing those one-to-one substitutions with that, you would arrive at this equation I show here. dTdV at constant s is equal to minus, that minus arises from the minus in the TDS relationship, dPdS at constant v. And you could do that with all four of these equations. And so I'll go ahead and show what those are. And you could go ahead and do that on your own and verify that you could come up with those equations. And again, I've color-coded these, so the green relation comes from the green equation, etc. These four down here on the bottom are called the Maxwell relations. And the reason that they're useful, for example, let's look at this green one here. What's useful about this green one? Well, what this tells me is that a change in entropy with volume at constant temperature is the same as a change in pressure with temperature at constant volume. Well, remember, we don't have entropy meters. We can't go buy one of those out of a catalog. And so we don't know how entropy would change with volume, even when I was holding the temperature constant. But it's really simple for a substance to measure changes in pressure with temperature at constant volume. That's really simple. We just need a thermometer and a thermometer and a pressure gauge, put it in a constant volume tank, make those measurements, really simple and easy to do, and we know how the entropy is changing. And that's what actually makes all four of these Maxwell relations really useful, is that we can go ahead and determine changes in entropy, which is not really easy to do with things like changes in pressure, temperature, and volume, which is much easier to do. So there's the power of the Maxwell relations. We're going to look at one other thing we can do with a Maxwell relation, and that's we can develop what's called the Clapeyron relation, or the Clapeyron equation. And the Clapeyron equation is used to answer this question: what's the approximate enthalpy of vaporization for material? Now, we could go in the lab and just completely vaporize it and measure how much energy that took, but the question I want to say is, could we do it with just PVT data? If I just gave you the pressure, volume, and temperature data, could you determine what HFG is? Because that would be the enthalpy of vaporization. And you can actually do that. And so we're going to see how we can do it using a Maxwell relation. The one we're going to use is this one I show in green, which says the SdV at constant T is dP dt at constant V. And what I'm going to do is I'm going to apply this at a particular location. I'm going to apply this during phase change. All right? You can apply the Maxwell relations at any point. You can apply it for any materials. There's no stipulations on that at all. They just need to be simple compressible materials. And so I'm going to apply this at phase change. So up here on the right, I show a PT diagram for material. And then I've got my, over on the far left, at low temperatures and high pressures, I have my solid. And at low pressures, high temperatures, I have my gas region. And up here I have my liquid region. And we show the saturation lines. And so you can see here's the vaporization line, here's the melting line. And what we want to know is, what's the enthalpy as we go across from the liquid to the vapor side? And so I'm looking at this line right along there. So I'm going to be applying this relation at that point there, which is the saturation point. And so the pressure at that point, well, P sat, is actually a function of T sat. And we know that. During phase change, pressure and temperature are not independent. And so we can say P is only a function of temperature. It's not a function of two variables. So therefore, the partial derivative, the PdT, is actually the total derivative if applied at saturation. So that's why I've changed from the curly D's to from the script D's to the regular D for dPdT at constant saturation. All right. Now we're going to do some other manipulations here. Is that, well, since we know dPdT at constant V is the same as dSdV at constant T from a Maxwell relation, and if we apply that also at phase change, well, the change in entropy as we go from the liquid to a vapor is this: Sg minus Sf, and then the volume is going to be Vf, or Vg minus Vf. And so that right there, those quantities right there, is dP dt at constant sat. And so what we're going to do is we're looking at the slope of this curve right up here. That's what dP dt is. And we're looking at that slope, and we're saying that's equal to the change in entropy over the change in volume. Well, again, changes in entropy aren't easy to measure, but we can do another substitution. I'm going to use this second TdS relation that says dH is TdS plus dVp. And, well, we're going to go ahead and do this at a constant pressure, so that second term is going to be 0. And so what this tells me is that ds is equal to, I'll bring t to the other side, dH over t. And so that right there is essentially equal to SFG. Oops, let me write that a little bit clearer. Sorry about that. All right, so what that tells me is that HFG over the temperature is essentially equal to SFG. And so now I'm going to go ahead and plug that in over there, and I end up with what is finally my Clapeyron equation, which says that the PdT at saturation is equal to the enthalpy of vaporization divided by T and VFG. And the reason that's useful is these, again, I've got pressure, temperature, and volume numbers. Those are all fairly simple to go ahead and measure, and that's giving me an estimate of what is HFG, or the enthalpy of vaporization. So let's go ahead and apply this, right, in an example, right? And so here what I've done, I've just taken the PVT data for water, and so this is just a small subset of it. And so if you look in the first column, I have pressure, second column temperature at saturation, and then my VF and VG values. And what I'm going to do is I'm going to go ahead and I want to estimate what is HFG. So I'm going to estimate dPdT at saturation. So let's just take these top two lines and we'll do an estimate. So dP would be about delta P, so we're going from 800 to 850, so we're doing about 50 kPa. And over that, the temperature changes from 172.94 and 170.41, so that would be 172.94 minus 170.41. All right, and that right there is equal to HFG, which is what I'm trying to estimate, over the temperature. And so I'm going to get, well, eventually the approximate temperature between 170.4 and 173. I'm just going to say that's about 172. This is all an approximation. So, and then that should be an absolute, so I'm going to add 273 to it. And then I've got to do this over VFG, and again, it's going to be somewhere between these two values, and I have 0.2269 and 0.2403. The VF values are really small. This essentially comes out to be about 0.23 would be the average minus, about 0. It's pretty inconsequential. And so now let's go ahead and look at what this number right here would be. And so I'm just going to go ahead and calculate what HFG is. And if I plug all those numbers in, I find out HFG is about 2018. And units on that are going to be kilojoules per kilogram. Right? So there's my estimate of what it is. And we actually, our table is also the actual value. And so if we look up here, and so these are my HFG values, well, it would be somewhere in here. And it should have been somewhere between 2039 and 2048. So it really should be something like, I don't know, 2043. So let's go ahead and let's see what my error is. So 2018, it should have been about 2043. Normalize that by what it should have been, which was 2043. And that right there is about 0.12. Or I got a pretty good estimate. I got an estimate within 1.2% using the Clapeyron relation. So that's pretty useful. I mean, again, we're just doing approximations, but within 1.2% with all the approximations, and I do a lot of approximations and rounding in my algebra out there. That's pretty good. So there's another example of where the Clapeyron, or where a Maxwell relation, in particular the Clapeyron relation, is pretty useful.